Hello, and thank you for coming today. My name is Evan. I am a junior level electrical engineering student at MSU Denver, and I am also a supplemental instructor for AC/DC circuit theory and tutor in this content area as well. I met Daniel last semester. We were in our DC circuit theory class together. And he had asked me to prepare a video over DC circuit series parallel combination circuits. So I'm going to go ahead and just jump right into content here. So I'm going to draw a pretty basic circuit just to give you the idea of like how to solve these and give you some of the formula options, and then we'll start working with some examples from the book and then some more complex examples, and that should round out our hour. So we have, let's say, a 5-volt power source here, and we're going to put a resistor here, and we're going to put 3 resistors in parallel here. We're going to have this return to ground. And for the sake of easy math, we're just going to make these all 10 ohms, just so this way you can see the idea behind the formulas. Pretend that these are drawn better and these are just full nodes. I'm drawing on my screen here, so it's going to be a little messy, but it should be legible. So in order to do a series parallel combination circuit, the first thing that we need to do is the goal, I should say, is we want to find the current and the voltage at all of the different resistors. So the first thing that we want to do here is we want to combine this to find the total resistance in this circuit, so that way we can find the current passing through, because as we know, current is the same in series. So if we can find the total resistance, then we'll be able to find the total current, and we can go from there. So the first thing we're going to do is we're going to reduce this parallel section here into one equivalent resistor. So the formula we're going to use for that is, well, the notation I'm going to use is I'm going to say RP, P standing for parallel, equals 1 over the sum of each of the resistors in parallel. And I'm going to pull out my calculator really quick to be able to crunch this number. So we have 0.1 plus 0.1 plus 0.1 to the negative 1 power, which is going to give us 3.33 ohms, approximately. I'm going to not go forever on this. So we could redraw this by looking at this red section and saying this is 3.33 ohms and ignoring this, right? So then what we're going to do, I'm going to get rid of that just for a second, just so you can see what's happening here. So what we're going to do is we're going to add this to this one. So that way when we have this and this together, it's going to give us our total equals 10 plus 3.33 is going to give us 13.33 ohms, okay? So this is going to be our total resistance. Now to find the current, we're going to go back to Ohm's law, right? Something I hope we're all familiar with at this point. So our Ohm's law is going to say I equals V over R, which equals 5 volts divided by 13.33 ohms for RT, right? IT equals VT over RT, total voltage, total resistance, total current. So this is going to give us 5 divided by 13.33, which is going to give us 375 milliamps. Okay? So, since I know current is the same everywhere in series, I can say that the current at this resistor is 375 milliamps, and I can also say V equals I R to find the voltage across that resistor, which is going to give us 10 times 0.375 equals 3.75 volts. And then we can also find the power by saying VI, which is going to give us 3.75 times 0.375 equals 3.75 times 0.375. This is going to give us 1.41 watts at that resistor. Okay, give me just a second here. I want to be able to make this a little bit smaller and scoot it over. Okay. Now, since I know that 375 milliamps is here, I know that 375 milliamps is going to flow over here. Before we get to current, let's talk about voltage at all of these resistors, okay? I'm going to do my voltage in green just for a second here. So my voltage is going to go around through here, right? Well, we know two things about voltage. First, we know that all the way around here, if we add up all of the voltages together, it's going to give us 5 volts. And we also know that voltage is the same in parallel. So all 3 branches of this, even if they weren't the same resistor values, they would all 3 give us the same voltage in parallel, or the same voltage across them, right? The current is what's different. In this example, they're all going to be the same, but the current is going to be what's different. So here's what's going to happen, okay? I'm going to take V total minus VR1. I'm just going to title him really quick. R1, VR1, VT minus VR1 equals VP, voltage for the parallel section, right? So we're going to have 5 minus 3.75 equals 1.25, voltage parallel, right? So now we know there's 1.25 volts across all 3 of these. So I'm just going to put that right here, 1.25 volts. I'm just going to show that by saying that's here, here, and here. And it's DC, so we can draw directions. We're going to call it conventional flow, so we're going to say from positive to negative. So we have 1.25 volts. Now, there's 3 ways that we can go about solving for current in parallel. The first one, before we do any of this, I'm going to give these numbers. This is going to be R2, this is going to be R3, this is going to be R4, okay? The first one we have, and I'll do this in red, is called the, or actually I'll go to blue because that's what we did last time. No, I'll do red. We'll do the voltage divider rule, okay? Or the current divider rule for parallel circuits. So, the current divider rule says I, R2, the current at resistor 2, is going to equal the total current, oh, come on, is going to equal the total current, screen behave, please. I'm in the middle of something important. Please do what you're supposed to. Okay, so total current is going to be source current, which is going to be 3.375, because remember we're in milliamps, times the RP, which is going to be 3.33 ohms, divided by the resistor we're looking for, which is going to be 10, equals 0.375 times 3.33 divided by 10. That's going to give us 1.25 milliamps. Okay? Now, here's another way we can use. We can use Ohm's law. So we could say IR3 equals VR3 over R3, because I equals V over R, which is going to give us, we said the voltage in parallel was 1.25 divided by 10. This is not 1.25, this is 125. Equals 125 milliamps. Now we also know the other thing that we can say is that in a node, nodes store nothing. So if we have 375 coming in, we know that the current here, the current here, and the current here, so the current at resistors 2, 3, and 4, all together have to equal the total current moving through the circuit, right? So we can say IR4 equals IT minus IR2 minus IR3, which is going to be 375 minus 125 plus 125. Because I put these in parentheses, so if I distribute this negative, it's going to be the same, which equals 125 milliamps. Now, because we have the current, we can use this same equation over here, VI. All three of these are going to have the same power dissipated, which is going to be 1.25 times 0.125, right? And then we can find the power. But now that we've gone over like this super basic example of showing the basic ways to go about this, I'm going to use some of the examples from your textbook. So I'm going to go ahead and close this out really quick. Sorry about that. Looks like I'm going to have to record this in pieces. I am new to making recordings, so please bear with me as I go through this process. I don't have the best software for this. It's just the software that's built into the computer. You just hit the Windows key, Alt and R, and it starts recording on your screen. But when I closed out the window, it thought I was done recording, so I guess that's where we're going to have to do this. This is from your textbook. It's from Unit 8, page 193. I got this book from Daniel, so I don't know if this is the teacher's edition, if this problem's on a different page for you or not. But what we're going to do here is we're going to talk about the resistor color codes, right? Because the first thing I want to do is I want to identify all of these resistors. And we're going to ignore the 4th band and 5th band because these only give us 3. So we're just going to assume that these were manufactured correctly and that there's a 0 tolerance on any of these resistors. So everything is manufactured perfectly. I have this image here of this handy dandy chart, which shows us 1st band, 2nd band, 3rd band multiplier. So these are 3-band resistors. Okay, so 1st band, 2nd band, 3rd band, those are the colors, right? 1st band, 2nd band, those are going to be your 2 colors times the multiplier. 4th band is tolerance, which we're going to ignore. So this chart, I'm sure, is either posted in your classroom, somewhere in the book, blah, blah, blah. Personally, I use an app for my phone that's called the Resistor app. And that app is really handy because basically it has this picture here, but then it lets you select them and it does the math for you. So if for this one that's pictured, for example, we would have green, blue, yellow, which is going to be 56 times 10K, right? So this would be 560K. Which if I'm going to check it on my app to make sure it's the right way. Green, blue, yellow. Yep, 560K. So that's how this works, right? So if I go here, let me just erase this really quick. If I come to this picture, okay, now I have this open. We shouldn't have this problem again until the end. Worst case scenario, Daniel, I'm sorry. I might have to send you a couple videos, but okay. So we now have all of our resistors, so we can start doing math. Yay, math. So I'm going to make this a little bit bigger just so we can write. So the first thing I want to solve for, because I know I have DC amps of 250 milliamps going through this whole circuit. So the first thing I want to do, very first thing I want to do, is I'm going to number these. They're already numbered. R1, R2, R3, R4. Okay? So what we have, and this is the proper notation to write this, is we have R1 plus R2 parallel with R3 plus R4. So what this is saying is that R3 and R4 are in series, and those two together are in parallel with R2, which you can see here, which is in series with R1, this whole parallel branch. So I'm going to do some algebra here really quick. So what we're going to do is I'm going to plug in some numbers. So we have 120. Let me change to a different color so you can read this a little bit better. Let me do pink. So we're going to erase here really quick. Okay. So I have 120 plus parenthesis 270 in parallel with parenthesis 68 plus 91 and parenthesis, right? So the first thing I'm going to do is 68 plus 91, which is going to give us 159 in parallel with 270, parenthesis, this is a parallel, plus 120. So now I'm going to do this combination over here, which is going to be 1 over 270 plus 1 over 159, which is going to give us, give me just a second here, I will do this on my calculator, 100.0. So we have 220 ohms total. So I'm going to put this right here, 220 ohms. Okay? Everybody good? Give you a second to write it down. Okay. Now I'm going to erase this. Now, the next thing that we need is we need to find our total E. E and V are the same. E is for energy, V is for volts. Either way, it's the same measurement. It's just a notational thing. Some people prefer one or the other. So what we're going to do is we're going to do Ohm's law. V equals IR, right? And since this is connected before the parallel section, current is the same in series. So we can say the total current for this is 250 milliamps. So we're going to say 0.25 times 220 ohms is going to give us 55. So this is going to give us 55 volts here. That's our power source. So I'm going to go ahead and erase this really quick. Everybody good with Ohm's law? Very basic. Okay. Now, here's the next thing I'm going to do. I'm going to change this to, let's go with the screen, just because I like different colors. So let's just fill out the rest of this area first, the totals, right? So this is going to be 250 milliamps power. P equals VI equals V squared over R equals I squared R, right? You can use any of these formulas based on what you have. Since we have all three, the easiest one is probably VI, which is going to be 0.25 times 55, which is going to give us 0.25 times 55, 13.775 watts. My program I'm working with right here won't let me write in these white spaces, so that's why I have this down here. but this is going to be 13.75 watts. Okay, be careful of your units. See how here I have volts, here I have milliamps. This is 0.25 amps. Okay, that's what this is saying over here, DC amps, 0.25. And I have my power total is going to be 13.25 watts. Generally, 9 times out of 10, you're going to compute power last. The only time that's not going to be the case is usually when you're given power, and then you have to like reverse it. But more often than not, you're going to do power at the very end. A lot of the times it's just this P equals VI equation. So a lot of problems don't ask you for it because you just do Ohm's law and all the different properties, and then you get your power at the end, and then you're just good with the power. But now what we're going to do is we're going to work on this first resistor, okay? Because this is the easy part. So he's easy because he's just outside of the parallel, okay? There's a lot of different ways to go about doing these types of problems. You can do voltage divider rule, you can do Ohm's law, you could do, we're just going to do Ohm's law. I think it's the easiest. The voltage divider rule, though, just so you know, I'll put it up here. V of Rx equals Vs over Rx over RT, right? This is the voltage divider rule, where this is your voltage source. This is resistor total. This is the resistor you're looking for. And this is the voltage at that resistor. Okay. This is the voltage divider rule. I don't want to have to compute this yet, though, so I'm just going to use Ohm's law because we already know that V equals IR, and we already know the current there is 0.25, so I'm just going to do that times the 120, which is going to give me 30. So I know that my voltage here is 30 volts, my current is 250 milliamps, my resistor is 120 ohms, and then my power is going to be P equals I squared R equals VI. We'll use VI, which is going to be 30 times 0.25, which is going to give us 7.5. So we'll have 7.5 watts of power here, okay? Now, here's the next part. And you kind of have to remember your rules to be able to do this quickly, right? But I'm going to do a little bit of cheating. I'm going to show you the easiest way to solve this problem. And it's going to be almost entirely Ohm's law as long as you remember all the other rules, right? So, and this is the key, is you have to remember your rules. If you don't remember your rules, you're not going to be able to take some of these shortcuts. It's going to take you longer to solve all these problems. So, we know we're going to look at resistor 2 now. We know he has a resistance of 270. We know that he has a voltage of 30 volts. Or not 30, sorry. Don't know that yet. We're going to take, to find the voltage in parallel, we're going to take the source minus this voltage is going to give us the voltage here, which is going to be the same as the voltage here, right? Because we know that voltage is the same in parallel. So we don't have to do any type of divider rule. We're just going to do this one right here. So we have the voltage here is going to be 55, because that's what this one's is, minus this, 30 equals 25 volts. So we're going to have 25 volts. Then we're going to do Ohm's law. V over R equals I equals 25 divided by 270 equals 0.25 92.6 milliamps. Okay? And then we're going to do power. P equals VI equals 25 times 92.6 equals, I'm sorry, not 92.6. See, I just caught myself. I forgot that that was milliamps times 0.0926. Don't forget that. This is a big mistake that a lot of people make all the time, myself included. And this is going to be 2.315 watts. So we'll say 2.3 watts, just for the sake of me having to draw it on the lines down here. Okay? Now, here's the next thing. And we don't have to use the current divider rule for this either because we were given this source current. We figured this out from the beginning. We know this point is not going to store any current. So we have 250 milliamps flowing in, and we have 92.6 milliamps flowing out. So that is going to give us, and I will switch to blue, something coming out over here, right? So we'll say 250 minus 92.6 is going to give us 157.4 milliamps. That's too hard to read. Let me change that to a different color. Purple. 1, 5. I wrote that on the wrong line. 157.4 milliamps. Okay? Now, 157.4 milliamps, right? Now, what else do we know? This is 68 ohms. Ohm's law, V equals IR equals 0.1574 times 68 equals 10.7. And let's just do power while we're at it. P equals VI equals 0.1574 times 10.7 equals 1.68 watts. Don't forget to not mess up your units, right? See, I have 0.157, that's 157.4 milliamps right here. Okay? Easy peasy. Now, what else can we say? We know that the voltage on both sides of this have to equal each other, right? So, or I'm sorry, the voltage on both sides of this have to equal each other. So the voltage here and the voltage here have to be the same, right? So we know that the voltage here is going to be 25 minus the voltage here, which is 10.7, which equals, boop, 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 boop. What does that equal? Calculator, 14.3. So we know that this is going to be 14.3 volts. We know that this is going to be the same as this because they're in series. So we're going to have 157.4 milliamps. We know that this resistor value is right here. We calculated that earlier. It's going to be 91 ohms. And then we know our power is VI, which is going to equal 14.3 times 0.1574, which is going to equal 2.25 watts. 2.25 watts. Okay? And that's everything for this. This problem is solved. We have all of our known possible measurements at all of these various locations. And this one was kind of a little tricky because they didn't give us this voltage source at the beginning, but we have all of our blanks filled out. And that's pretty much it. The thing you got to be careful about here is making sure you analyze the circuit properly. So at the beginning, when I did, just to review, it was R1 plus the rest of this in parallel, R2 parallel parentheses R3 plus R4. Remember to put in your parentheses, because if you don't, you're just going to have R1 plus R2 parallel R3 plus R4, and people are going to think your circuit looks like this. And this is not what we have. So don't forget your parentheses, because this would be R1 plus R2 parallel to R3 plus R4, right? So hang on for the next section of the video, because I'm going to go over a more complicated example on how to write this, just to give us a break from doing these types of problems. And then we have one more of these, and then I'll have some final remarks for you. Okay, so as you can see here, we have a slightly more complex problem, right? So this is going to be a little tricky, okay? Because what I want to do is I want to zoom in just so we can see it better, right? It's not quite necessarily straightforward, the best way to talk about how to look at this. But if we take a little bit of time, we can see that everything's going to come out from here, right? Ooh. Okay. Then some of it's going to go this way and down, and some of it's going to go this way, and then it's going to come here and go up. And then we'll do the rest of these in green. And we see that this guy's in parallel, right? We see the other option is this way and back. But we see there's another option, which is from this way and back, right? So let's do the yellow first, right? Because this is all in parallel, so we'll do parentheses R5 plus, these are in series with each other, so we have R7 parallel R6 plus R8. All of this could be viewed as one big node. Don't get messed up by this wire. This doesn't matter at all. And we're going to say this all plus the other half. So we'll say R1 plus R2, or not plus, sorry. This is not plus this. This is all in parallel with all of this. R1 plus R2 plus parentheses R3 parallel R4 and parentheses and parentheses. So to write this all out along the bottom, which is what I should have done at the beginning, so you can see this all on one line, we would have R5 plus R7 parallel R6 plus R8 parallel R1 plus R2 plus R3 parallel R4 end. And we'll put this in parentheses too, just to make it clear. So this way we can see this whole side, then this whole side. So the way we would reduce this, and I'm not going to waste our time doing all this number crunching, is we would do these together first, then add these three together, then do these two, then add all three of these together, then parallel connection, then RT. Okay? See, it kind of becomes more complex the further and further you go. Then, next thing you know, you've got 10 different types of components connected in all these different nasty types of combinations, and the next thing you know, you're looking at a schematic for a computer. But to start, I can't imagine that you're going to have to do anything that's more complex than this problem. The reason that I brought this problem up was just because it's a good example of recognizing the notation, because this is really all it boils down to, is analyze the circuit, determine what's in series, what's in parallel, and work your way from the inside out. So start with your innermost parentheses, do your parallel, 1 over 1 over equation. You can also use this other one, which will have R1 times R2 over R1 plus R2 when you have R1 and R2 in parallel with each other. But I prefer the 1 over R1 plus 1 over R2, because then you only have to remember one formula, because these are equal to each other. But if I throw in a third resistor, you just add it in right here. You cannot do this. This does not work. It's only this one. This only works for 2 resistors. So this is the formula. Let me just highlight it. It's just this highlighted section. Nothing else. This is a shortcut. They call this the shortcut. I prefer this because you only have to know one formula and you can add plus, 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 blah, blah, blah if you have inside of your circuit, you have 10 resistors in parallel, you can just use this one formula and you could be good. So I'm looking at this now that I've just written all this, it looks a little manic. I think that's funny. But you can use this formula highlighted in blue. I prefer the circled one. Do whatever makes you happy. See you in the next clip. And this is the final section of our video series. So I'm just going to go over this one again, just like how I did the last one, only this time, instead of pulling up the other graphic to show you how to find all these values of the resistors, I'm just going to plug them all in my phone just for the sake of time, because I already showed you how to do it, and why bother beating a dead horse, right? So anytime I get a problem that has these types of pictures in it like this, I always use the first thing I always do is find the resistance everywhere. It just makes your life that much easier, right? So this orange, orange, orange is a 33K resistor. This green, brown, orange is a 51K resistor. This orange, white, orange is a 39K resistor. This, I'm going to call that a red, because this looks a little different than this. And sometimes this can be tricky, discerning the colors. It can be in real life too. So a lot of the times they'll tell people to make sure that you test the resistors with your multimeter before you actually use them. A lot of times they get put back in the wrong place too, or they become less effective over time. So for here, we're going to call this 24K, because we're going to call that red. Okay. Now, this is showing me volts DC. This is showing me volts DC 8.00 from here to here, which tells me this has 8 volts. That's all we're given for this problem, okay? These are all of our knowns, right? What's the first thing I want to do? I want to find my current here. This is going to be the easiest because we have 2 variables, right? So let me go ahead and make this a little bit bigger, and I can work off into the side here. So we have 8 volts, 24K ohms. So I equals V over R equals 8 divided by 24K equals 8 divided by 24,000 equals 333 nano, or not nano, micro amps. Micro amps. This symbol, I don't know if he's gone over with this or not, is a mu. That's what this is called. It's a Greek symbol. It's a Greek M. They have a tail on both sides. It kind of looks like an M here, but we draw it like this, right? At least I do. But it's supposed to be an M, right? M for micro, but we don't use regular M because regular M is milli, so we use Greek. We use this mu symbol for micro. So we have 333 microamps, right? So I'm going to go ahead and write that in here. 333 microamps, right? And then while we're here, we'll just do power. P equals VI equals 8 times 333 times 10 to the negative 6, because that's what that micro means, right? So 8 times 333 times 10 to the negative 6. Sorry, I've been repeating things. I say them out loud as I type them into my calculator, which you cannot see given this format. But this is going to give us 2.664 milliwatts. So 2.664 milliwatts. Okay, this portion is done. Sometimes I like to just do everything on one resistor. It's easier that way. Sometimes not so much. This problem, this way, this is how we're going to do things. So, what's next? Okay. So, what do I know about current in series? Current in series is always the same, right? So I know that the current here is going to be the same as the current here. So I'm going to make this 333 microamps, right? Because I know that they have to match, because current is always the same in series no matter what. No ifs, no ands, no buts. Do not pass go. Do not collect $200. That's just the way it is. Okay. So V equals IR, right, for voltage here. So 333, 10 to the negative 6, 51, 10 to the 3 for the K. 333 times 10 to the negative 6 times 51 times 10 to the third, which is going to give us 16.983. So we're just going to round that to 17. Just for the sake of easy math, 17 volts. P equals VI equals 17 times 333 times 10 to the negative 6 equals 5.661 milliwatts. Okay. Now, here comes the fun part. So how are we going to figure out what's going on this other side, right? There's a very famous configuration that this circuit kind of reminds me of. It's not quite this. I don't know whether or not you touch on this in your class with Daniel or not. There's a very famous configuration known as a Wheatstone bridge. If you were going to connect this in the middle, which is typically drawn this way. This is called a Wheatstone bridge. This reminds me a lot of this, but we're just going to continue through here anyways. We'll talk about that later, maybe. I don't know whether or not you guys cover that, but this kind of reminds me of that. So, what do we know about parallel circuits? We know that they have the same voltage. on both sides. So the voltage here and the voltage here is going to be the same. If I was going to connect this here and this point here, it would give me the same reading if I connected this point here and this point here as well, right? I don't know exactly how this meter works, so I may have connected these to the wrong spots on the meter, but you get the point. This side and this side have the same voltage. So I'm just going to erase this stuff really quick. And we're going to say that the voltage here is going to be 8 plus 17, right? Which is going to be 25, okay? So we can put this over here. We can say that our total voltage is 25 volts. And give me just 1 second. I'm going to pause the video and then continue. Okay, so continuing. Sorry about that. I was interrupted. I'm in a classroom on campus that I just kind of snuck into. And I said, I'm just going to post up in here and make this video anyways. So sorry about the interruption, but moving forward. So we have 25 volts here. So that means we have 25 volts here, right? So we're going to use a voltage divider rule this time because it's just going to make our life a lot easier. So if we say VR1 equals 25 times 33 over 33 plus 39, right? This is going to give us the voltage here, okay? So I'm just going to go ahead and crunch this in my calculator. And that's going to give me 11.45, so we're just going to call that 11.5. So we're going to call that 11.5 volts. And then I'm going to take 25 minus 11.5, and that's going to give us 13.5. So that's going to give us 13.5. I always do this, by the way, on my exams. Anytime I have a math problem, I always put a box around my answer. It makes things pop out more than just circling them if I actually draw a box. But anyways, moving forward. We are going to calculate current now, okay? So current is easy because we have voltage and resistance, so we can just say I equals V over R, and we'll just do the resistor 1 just for the sake of it being first. So we'll say 11.5 divided by 33K, which is going to give us 11.5 divided by 33,000 is going to give us 348.48. So we'll just say 348 microamps. So we have 348 microamps. Now what do we know about current? It's the same in series, so the current in both of those is going to be the same. So we have 348 microamps. If you don't believe me, you can see what 13.5 divided by 39K is on your calculator. But I bet you it's the same as this one. So anybody want to take that bet? I'll bet you that if it's not the same, that you have to pay my college tuition. So moving forward, we just have a couple more power calculations, and then this one is done. So power, P1 equals V1 I1 equals 11.5 volts times 348 times 10 to the negative 6 for the micro. 11.5 times 348 times 10 to the negative 6 equals 4.002 times 10 to the negative 3. So we're just going to call that 4 milliwatts. And then over here, we have P2 equals V2I2 equals 13.5 volts times 348 times 10 to the negative 6 equals 4.698. So we'll call that 4.7. I'm not exactly sure how many decimal places you're supposed to go to. You're going to have to ask your teacher about that. because everybody's going to give you a different answer. Just go based on whatever your professor likes. Different teachers and professors and instructors and lecturers, depending on their title, and not all of them of the same rank, but all of those different types of people, they all have different rules onto what they actually like, okay? So just listen to what they have to say. So we have voltage total. Now all we need is current and resistance and power total. And there's a lot of different ways to do this. But what I think is probably the easiest is I'm going to go current first, just so that way I don't have to deal with the resistors equation. So, because this is just going to be simple addition. So I can say IT equals I1 plus I3. The current here, this arrow, is going to equal this current plus this current. Because these are going to meet together, and they're going to come over here, and everybody's going to be happy. So this is the equation you can use for this type of problem. It's going to make your life so much easier. Okay? So I'm going to say this is equal to 333 microamps plus 348 microamps, which is going to equal 681 microamps. So we'll put that right here. And then for my resistors, easiest equation of all time, Ohm's law, V equals IR, which means R equals I divided by V. No. V divided by I, which means 25 divided by 681 times 10 to the negative 6 is going to give me my RT. Is going to be 36.7K ohms, which we're going to check, okay? I'll teach you how to do this the other way too. So if we took R1 plus R2 in parallel with R3 plus R4, we're going to get 33K plus 39K in parallel with 51K plus 24K, which 51 plus 24 is going to be 75. Make that prettier. 75K parallel. And this is going to be 72K. And then we'll have 1 over 72 plus 1 over 75, which is going to be give me just a second. These ones take a little bit longer to type into the calculator. $36.7K, which tells us that all of these were done correctly, right? And I use this based off just these resistor values here. So if these are right, that means that all of these are also right, okay? Final thing is power for this problem. So P equals VI, which equals 25 times 681 times 10 to the negative 6. 25 times 681 times 10 to the negative 6 is going to give me 17.025. So we'll just call that 17 milliwatts. Okay, and that's this whole equation. So final remarks. I'm just going to write some formulas up here so that way you have them. Just to make your life easier for next time, because this covers all of the things that were covered in the problems at hand, but I just want to take a couple extra minutes at the very end here to go over my formulas. I have another meeting I'm going to jump to, so I'm going to cut this and make that last little section in just a minute. So stay tuned, and I will see you soon. And for the final piece of this saga, this hour-long journey of math and circuit analysis, I am going to just write some formulas down, just the main things that we used today. I had to leave for an hour meeting, but benefits of being able to record this in snippets and piece it back together. I hope it doesn't look too choppy between the pieces when it's done, but anyways, moving forward. So some of the things that we used today were, for example, Ohm's law. So we have V equals IR, I equals V over R, R equals V over I. We also have power stuff. So P equals VI, P equals I squared R, P equals V squared divided by R, right? Okay, now we also have the voltage divider rule, which is where we have two resistors in series connected to this guy, right? We have VRX, for whichever one we're looking for, is VS, which is the source of RX over RT, okay? So even if we had like parallels here, we would solve this by reducing this to one resistor and then doing this equation, remember? Next piece we have is the series circuits. So RT equals R1 plus R2 plus R3, and this is for series. Then we also have parallel rule, so RT equals 1 over R1 plus, no, we have 1 over R1 plus 1 over R2 plus 1 over R3. We also have right? Okay. Then we also have the current divider rule. So we have IRX equals I times RP over RX. Now, one thing here that is important to note is that if I have three resistors in parallel connected to a voltage source, this I would be the I coming into all three of these. So I'm going to have I1, I2, and I3, right? But remembering they all come around, right? So this I is whatever is flowing into your node, okay? This is the I you use here. Now, RP goes on top, RX goes on the bottom. The current at the resistor you're looking for, that resistor goes on the bottom here, not the top. Over here it goes on the top because RT is always going to be greater than RX. But over here, RP is always going to be less than RX. You'll know it's wrong if your current ends up bigger, right? If you don't end up with a bigger current, if you end up with a smaller current, that means you did it right. Because we're not pulling milliamps out of thin air. Just like how we're not pulling volts out of thin air. So the voltage equation and This is called the voltage divider rule. These three are Ohm's law. These are power. These are both this is the voltage divider rule. And lastly, we have our current divider rule. And that concludes our hour. That should cover pretty much everything you need to know about series parallel combination circuits. Just remember to watch your parentheses, analyze the circuits properly, and crunch your numbers. That's the biggest thing. I would say more so than anything else is just really make sure you analyze your circuit properly.